Welcome to a new lesson of the Haskell course. This one is about the applicative functor. We're going to cover why do we need applicative functors. Then we will learn about function application at the functor level and about being pure. And after that, we will be ready to actually define the applicative type class and explore its laws. Once we understand the concept and use of applicative, we're going to explore how do we program with effects. And finally, the extra functions the applicative type class gives us and how applicative is actually defined in the base library. Okay, so why do we need applicative functors to begin with? Well, let's explore our journey until now and do a recap of our abstraction journey for map and functor. We started with a bunch of recursive functions. These functions were useful, but they were limited to applying a specific function to a list of specific types. However, we noticed that they had common traits that we could extract, and we got the map function. The map function is a more powerful version of these functions because it's more general. Now we can apply any function to a list of values. And because it's more general, we can recreate the original functions by passing the concrete function we want to apply to the values. But then we faced a problem. Map only works for lists. But there are plenty of structures with values we want to manipulate. If we implement their own map-like functions, they will look like this. We realized that these functions were useful, but they were limited to specific structures. However, they had common traits that we could extract, and that's how we got the Functor type class. The Functor type class is a more powerful version of those functions because it's more general. Now, we can apply any function to any structure that is an instance of Functor. And of course, we can obtain what we had before and more by creating the instances. As you can see, every time we extracted a more general expression, we got a more powerful abstraction. But there are cases when functor is not enough. Let's try applying a few functions to a functor. Let's run this. As you can see with the first example, we have no issue f-mapping the function +1 to just 3. If we check the type, we get that it's a maybe int right here, maybe b, when b is a type that is an instance of the num type class. And if we actually apply +1 to just 3, we get just 4. But what if we want to add two functors? If we check the type of applying the plus operator to just 3, we get a function at the functor level, and we are not prepared for this. We can use fmap to take regular functions and apply them to functors, but we don't have a way to apply functions that already are at the functor level to other functors. In the last example, I did some juggling to get almost what we need. By using fmap multiple times, I managed to actually add the value just 3 and just 2 to just 5, but I ended up having duplicate nested functors. The worst thing is that this is a common scenario. We may want to add two optional values that we retrieve from our database. Or maybe we want to apply a function to combine 3 functors into one. It's more common to work with multiple functors than with a single one. So we need to solve this. One solution will be to create another version of fmap that can handle a function of 2 arguments. For example, like this. If we run this, we see that we create the fmap2 function that can take a binary function and 2 functors to generate a third functor. In the specific case of the maybe functor, we can pattern match both functors to check if both are just values. And if they are, we apply the binary function to both of the inner values and wrap it again in a just. For any other case, we will be missing a value, so we can just return nothing. There's nothing we can do. And it works! That will solve the problem. So in theory, we could create a type class called, for example, Functor2 that provides this fmap2 function. But that only works for binary functions. If we need to use function that takes 3 or 4 or more arguments, we will now need to create Functor3, Functor4, Functor5, etc., etc. You know where we're going with this. This method is unsustainable. It doesn't matter how many type classes you create, there's always a use case that requires one more parameter. And on top of that, we will have maybe dozens of type classes presenting the same concept. The concept of applying a function to the values of a structure without modifying the structure itself. But don't worry, thanks to currying, there's a better way. Let's talk about function application at the functor level. This is one of the two key ideas of this lesson. If you understand this section, the rest of the lecture will flow naturally. Okay, so we know that writing an fmap for every possible number of arguments is not feasible. But we don't have to. If we take a look at Haskell's function application, we see that function application takes a function that goes from A to B and a value of type A and returns a value of type B. It seems as if we could only apply a function of one argument to a value, but we know that in practice we can do, for example, this. Here we have the calculate function that takes 3 integers and performs a calculation. We can actually apply the calculate function to 3 different integers using 3 different function applications. And if we run it, we'll see that we get the correct result. So how does this work? Well, it's quite simple. Let's see step by step. Let's zoom out a little bit. I will use the $sign operator to more explicitly signify the operator that does the function application. But this is the same as if we apply the functions with the space as we did before. So we have the calculate function that takes 3 ints to return an int, and we have the function application function that takes a function that goes from A to B and an A to return a B. If we apply function application to calculate as its first argument and 3 as its second argument, then we'll have the type shown here. The first argument is calculate, so it's int to int to int to int, which we know that because all functions are correlate functions, this actually means that the calculate function takes 1 integer and returns a function that takes 2 integers to return an integer. So the type A is an int and the type B is a function that takes 2 ints and returns an int. So the final expression, function application applied to calculate and 3, gives us back a function that takes 2 ints and returns an int. And doing the same for the second case, we take our final expression of the prior step that we know its type, and we apply function application to that expression and a new int. That means that the first argument of function application is a function A to B, where A is int and B is a function that goes from int to int. So the second argument is an int, and the end result is a function that goes from int to int. And if we do the same for the final application, we have function application, and the first argument is this whole prior expression. And we know that this whole expression is of type int to int, so A to B now is int to int. The type it's applied to 4, that is of type int, so we get back an int. This is how function application works. So we know that function application can be used to apply functions that take any amount of arguments by just applying the operation again and again until the function is fully applied. And that's our solution. We want to create an operator that works like function application, but for functors. That way, it will work for functions of any number of arguments, and we can do it quite intuitively. If regular function application has this signature, how would the type signature of the same function will look if everything was a functor? Well, you guessed it, like this. We call this operator the apply or AP operator. We use an operator, of course, because it will be used mostly as an infix function. The type itself reflects that the behavior is the same as regular function application, but lifted to work at the functor level. It's important not to confuse the signatures of this functor level function application with fmaps. Fmap takes a function that is not at the functor level and applies it to a functor. Once you apply the function the first time, the end result, be it the final value or a partially applied function, is now at the functor level, so we cannot use fmap anymore. To make it more concrete, let's define it for the maybe functor. As you can see, it's quite simple. We have to pattern match to make sure that we actually have both the function and the value. Then, we apply the function f of type A to B to the value x of type A to get a value of type B, and wrap it again with the just constructor to get our final value of type maybe B. If we don't have both the function and the value, we cannot return a valid result, so we return nothing. This is really similar to the fmap definition, with the caveat that now not just the value is optional, but also the function. Now that we have our definition, let's try it out. So here we are trying to apply just plus 1 to just 3, and then we have the just plus function, and we want to apply it to just 3 and just 2, and finally we have the calculate function that we had before, that takes 3 integers and performs some calculations. And we want to apply just calculate to 3, and then apply it to 2, and then apply it to 4. And if we run this, awesome, it works. But I assure you that the apply operator is function application at the functor level. And I compare its type with the function application type to build my case. But I know that that's not enough to convince a scholar like you. So it's time that I prove it to you. To prove that the apply operator is actually function application at the functor level, I'm going to create a functor that doesn't do anything. If the structure doesn't do anything, then the apply operator should return the same result as regular function application, right? How a functor that doesn't do anything look like? Well, it's actually pretty straightforward. We need a type that wraps another type and doesn't provide any functionality. So, like this. Let's run it. Here, we have a new type wrapper of identity A that has a single value constructor called identity that holds a single value of type A. On top of that, we use record syntax to provide a function to easily extract the value wrap inside the identity type. So, if we have a type with only one constructor, the only thing it does is to hold the value inside. It's virtually the same as the underlying type, but with the extra annoyance of having to wrap it and unwrap it. We call this type the identity type for the same reasons we call the identity values and the identity function like that. They preserve the identity of the values they interact with. In other words, they don't do anything. But do you remember the new type wrappers of the semigroup and monoid lessons? Those were wrappers with a single constructor, but were not identities because of the behaviors we gave them when defining the semigroup and monoid instances. So now, we have to also implement the type class instances in a way that they provide no extra behavior. For our purposes, we only need the functor instance. So let's implement the functor instance for the identity type. And we can do that like this. To define the functor instance for identity, we just need to define fmap that takes the function, and then we pattern match the identity constructor to extract the value of type A, apply the function to the value of type A, and wrap it again with the identity constructor. It's the same as the just case of the maybe type, with the difference that because we only have one constructor, there's no option to fail. So we will always be able to apply the function to the underlying value. Let's try it out. So if we apply fmap plus 1 to identity 3, we get identity 4, times 2 fmap to identity 3 is 6. We fmap ignoring the value of the original identity and replace it with a different value if we get the correct value identity A. And finally, we verify that our instance follows the functor laws. So we check that fmapping the ID function to an identity is equal to the original identity value. And we get that indeed that's true. So it works as expected and it respects the functor laws. So we have a valid functor right here. Now that we have a functor, we can create the apply operator. The type was like this. We have a function at the functor level that we apply to a functor with values of type A to get the functor with values of type B. Because the identity functor is basically just an annoying wrapper, we know that we have to unwrap, then apply the function to the value of type A and wrap again. So we will just do that. We pattern match to extract the function and the value, apply the function to the value, and wrap it again. So let's run this. Pretty straightforward. It's almost the same as fmap. And now comes the moment of truth. Let's see if the apply operator is actually function application at the functor level. And we're going to do it by comparing the results of regular function application with the results of our new operator. As you can see, we have 3 examples of applying the same function to a value or multiple values, once without a functor and using the built-in function application, and once using the apply operator with a functor that doesn't do anything, the ID functor. So if we apply plus 1 to 1, this should give us the same result as applying using our new apply operator identity plus 1 to 1, and then getting the value inside the identity. Same for plus applied to 1 and 2, and same from a function that takes 3 arguments and multiplies the second and third and then adds the first applied to 1 to 3, should give us the same as the identity of that function applied to 1, applied to 2, applied to 3. So if we run this, we see that we get the same result in all 3 cases. We just showed that the apply operator is a generalized form of function application. It's more general because we get the same old and boring function application if we specialize our new operator to the identity functor, but we can also apply it to other functors. Is it enough though? Well, let's talk about being pure. We have shown that the apply operator is a generalized form of function application. Does that mean we could handle all possible function application cases while working with functors? Let's see. When working with functors, there are 3 possible base cases that combined can generate all possible cases. You can have everything at the functor level. If we run this, we'll see that there's no issue with that. It works using the apply operator we just defined. Another case is to have the need to apply a function that is not a functor to a bunch of functors. No issue either, that is what fmap is for. We use it to lift the function and then we keep going with the apply operator. So if we run this, we'll see that everything is okay. But we could also encounter a third scenario. When one or more values that we want to apply the function to is not a functor. This happens in tons of scenarios. For example, if 2 of the 3 values come from the database and the other one is provided locally, we have no reason to have the local value wrapped in a maybe type. We currently have no way to solve this for every functor. fmap lifts functions, not constant values. So we need a way to lift arbitrary values. This function that we need should take any value and return it untouched embedded in a functor. We could call this function lift because it lifts a value to the functor level. But for reasons I will explain in the second to last section of this lesson, we will call it pure. Regardless of how it's called, what it does is to lift values to the functor level. We can define it trivially for the maybe type like this. If we run this, we see that we can create the pure maybe function that takes any value and returns a maybe of the same value by just wrapping it in the just constructor. So pure maybe applied to the a character, get just a, and pure maybe applied to 4, get just 4. And having this function, we can solve the missing case like this. We can use the pure maybe function to lift the value 2 to the maybe level, and now we can apply the function using the apply operator. So if we run this, we get the correct result. Of course, pure maybe is specialized to the maybe functor, so it's the same as wrapping the value in a just constructor. We want a function that works for all functors. So this function, along with the apply function, will also be part of a new type class we'll create. And having this second behavior, we can apply any function to any amount of values at the functor level. To prove it to you, let's define fmap for all the functions from 0 to 4 arguments using these 2 new operators, like this. I remove the functor constraint to avoid cluttering the slide, but remember that all the type level f's are functors. So for fmap 0, we have a function that takes 0 arguments. That's a constant value. So we need to embed a constant value into a functor. Easy, we just use pure. For fmap 1, we have a function that takes 1 argument. We lift the function to the functor level and then use the apply operator to apply the function to the argument. For fmap 2, we have a function that takes 2 arguments. So we lift the function to the functor level and then use the apply operator to apply the function to both arguments. And it's the same for fmap 3, fmap 4, fmap 5. Lift the function and then use the apply operator as many times as needed until the function is fully applied. And as I'm sure you might notice, fmap 1 is the same as a regular fmap, and fmap 2, 3, 4, 5, etc. all start with the same pure of g applied to the fa pattern. Same as here, same as here, same as here. So we can simplify a bit by replacing the first application of the apply operator with the functor operator to avoid having to lift the initial function before applying it. So we get this simplified version. And that's it. We have proven that we only need the apply operator and pure to handle all cases. Plus, we can use fmap to make it more concise by avoiding explicitly lifting the initial function. So now that we have everything we need, I guess it's time to formalize our findings. Let's define an initial approximation of the applicative type class based on what we could figure out until now. So our initial approximation will look sort of like this. An applicative is a functor with a function to lift expressions called pure, and an operator that works as function application at the functor level, symbolized with this bracket star bracket, but that we call apply. So having this phrase that express our intent, we can define the type class applicative of f, where f has to also be an instance of functor, and that provides the pure function that takes a value and lifts the value to the functor level, now applicative level, and an operator that works as function application at the functor level, now applicative level. This is our initial approximation. This is not the final type class, but it already encapsulates the concept of applicative, and it's enough to define a couple of instances so we can have something to work with while we figure out the loss, because of course, applicative has loss. Let's start by defining the instance for identity. This is going to be pretty easy. Of course, because applicative is a subclass of functor, the first thing we have to define is functor. It's pretty straightforward. We just defined it a bit before, so we're not going to go over it again. But now that we have the functor type class, we can define the applicative type class. To create an instance for the applicative type class, we need to define both pure and the apply operator. We don't have much choice for pure. We need to lift a value to the identity level, and we have only one constructor with the same type as pure. So we just use that. For the apply operator, we have two choices. We can pattern match both the function and the value to extract both and then apply the function to the value and wrap it again in the identity. Or if you look at the definition of the functor instance, it already pattern matches on the second value and applies the function and wraps it again. So we can avoid repeating ourselves by just pattern matching to extract the function and then f-mapping the function to the identity A value. Both definitions do the same, but the second one takes advantage of the definition we already have of fmap. So we run this, so now we have the instance for identity. And now that we have this instance, we can use the operators. Identity plus 1, apply to 1, identity of plus, apply to 1 and 2, all the same three examples as before, but now using the instance, and if we run them, you can see that we get the correct results. And take a look at this. We are here using pure in both for the second and third argument to lift those two arguments to the functor and now applicative level. I know, that one was boring, but let's take it step by step. Now let's create an instance for the maybe type. Same as before, we start with the functor instance. We don't run this cell because these instances are already provided by the prelude. We already implemented the functor instance in the previous lesson, so we won't go there. But the applicative instance is a bit more interesting. We have to define pure and the apply operator. The apply operator is pretty straightforward. We do the same that we just did for the identity functor, and we pattern match the function, and because we have fmap at our disposal, we fmap the function to the value of type maybe A to get our final result. And in the case that we cannot extract this function, we just return nothing. But for pure, we have two options that satisfy its type of A to maybe A. We could create a function that ignores its input and returns nothing. Or we can just return just that fits perfectly fine by itself. Conceptually, it makes sense to use just because if we use nothing, we will always get nothing independent of the value we lift. But if that doesn't convince you, just is the only option if we want to respect the loss of the type class. Remember that one of the characteristics of functors was that fmap didn't change the structure itself, only the values. Here, the apply operator has the same restriction. Sadly, same as with semigroup, monoid, and functor, not everything is reflected in the type class definition. So we have to complement it with a few laws. Here they are. We have the identity law. Applying a lifted ID function to an applicative should return the same applicative. This makes sense, right? Same as when dealing with fmap, the apply operator should respect the structure of the functor that is now an applicative functor. Let's see an example with the maybe type. So applying pure ID to just 3 should be the same as just 3. And if we run this, we get that this is true. But if we use the wrong pure function that has the alternative definition for pure, we see that this is false because wrong pure applied to ID returns nothing and nothing applied to just 3 is nothing. So we get that nothing is equals to just 3, which is false. That's why we have to use just as the definition for pure. If we use a function like wrong pure that ignores the input and always returns nothing, we have the correct type, but we change the structure. Next, we have the homomorphism law. It has a weird name, but the law is pretty straightforward. Applying a lifted function to a lifted value should be the same as applying the function to the value and then lifting the result. This enforces that the apply operator has to behave as regular function application. Let's see an example. So we have our left side of type maybe string, and in this side we lift the function show with pure and apply to pure 3. So we lift show, lift 3, and apply the lifted versions of show to 3. This is this left side. In the right side, we apply show to 3 and then lift the result. Those two should be the same, and here we print the result just to see what we get back. And as you can see, both sides generate the same result, which is just a string of 3. Amazing! It works as expected so far, but we still have 2 more to go through. Next, we have the composition law. This one shows that the operator is associative, although it might not be evident at a glance. So here's an example. On the left side, we want to combine the show function with the times2 function and then apply the result to 3. And we know that the way of combining functions is by composition. So we lift function composition to the applicative level and apply it to just show and just times2. Then we apply the result of that composition to just 3. On the right side, we first want to combine the last 2 applicatives and then the result with the first. In this case, we don't need to lift function composition because we can apply just times2 to just 3 directly to get just 6, and then apply just show to get the string representation of the number 6. We get the correct results, and both sides return the same. Finally, we have the interchange law. This one states that we should get the same result if we flip the arguments when applying a function. We know this is true for regular function applications. For example, on the left side, we apply the function +1 to 3 to get 4. On the right side, we apply a function that takes another function as parameter and applies it to the number 3, and then apply that to the +1 function. This results in +1 being passed as a parameter and then being applied to 3. As you can see, we have to do the extra step of adding a lambda function, but if we flip the arguments of function application, we still get the same result. If we run this, we get the same result. That property should also hold for our apply operator. So we define the test. This is the same as we just saw, but lifted at the applicative functor level. Same as before, we have to do the extra step of adding a lambda function. But if we flip the arguments of the apply operator, we should, and we do, still get the same result. And that's it. Those are the applicative laws. To hone in on the type class implementation, let's do one more before moving on. Let's create the applicative instance for the either type. We already saw the functor instance in the previous lesson, so we will skip it. For the applicative instance, we use write to lift the value with pure. If we follow the types, write is our only choice. Lifting anything with the left constructor will be useless because it will make any function that uses it return left, regardless of the other values it's applied to. On top of that, it also makes sense from the functor perspective. Left E is part of this structure. We want to lift a value, so we have to use a constructor that can hold a value. And the only one available is the right constructor that can hold values of type A. And for the apply operator, we have to take into account the cases that the function is both left and right. If the function is a left, it means we don't have a function, we have an error. So we have no other option than propagating that error. If the constructor is a right, we do have a function. And in this case, we could have both left and right as second arguments. But we don't have to deal with that because we already defined fmap that does it for us. So we just fmap the function to the second value. And that's it. If we try to use it, we see that the results are reasonable. Plus apply to write 1 and write 2 gives me write 3. This function that takes 3 values and makes computations, apply to pure 1, left 2, and pure 3 returns left 2. And the same function applied to write, pure, and pure can actually perform the computation, and we get write 7. So our results are reasonable, but reasonable is not enough. We have to check if our instance follows the applicative laws. So let's do that, starting again with the identity law. We check the identity law for both left and right, and we see that it holds. Nice. Our implementation follows the identity law. Now we have to check the homomorphism law. Pure of +1 applied to pure 1 should be equal to +1 applied to 1 and then lifted using pure. Both are of type either eInt. And if we run this, it's true. Amazing. 2 out of 4. Let's do composition next. So in this case, the left side, I copied this same definition right here. And the right side, I copied the definition right here to make it more clear. And I defined the bindings in a where clause. So we have write +1, write times 2, and write 3. If we compose the first two and then apply the result to the third, should be the same as if we first apply write times 2 to 3 and then apply +1 to the result. So those left and right side should be the same, and if we do it, we get that it's true. And not only that, if, of course, we change any of these values to different ones, for example, v now is left some error, and we have to do the same here, so both have the same initial values. These two should also be the same. And of course, if we run it, it's the same because it returns in both cases left some error. So our third law still holds. Finally, we check the interchange law. If we apply u to pure of 5, should be the same as if we flip the arguments and apply pure of 5 to the function plus 1. Here we use the apply operator as a shorthand of writing the takes an f and produces an f. This is the same, and if I run it, I get that it's true. And if I do this, we get that we still get the same result. Amazing. So our implementation seems to follow all applicative laws. We now have the identity, maybe, and either applicatives under our belt. So I think it's time to move on to programming with effects. And I must say, congratulations, you now know how to program with effects. Oh, you didn't realize that? Well, you do. Here's why. When we talk about maybe, we say that it gives us a way to represent values that might fail. We wanted to return a value, but we weren't sure if we were going to be able to do so. So we used maybe. In the first example, we see how we can use maybe values to create a safe version of div that doesn't crash our program if we try to divide by 0. It just returns nothing. In the second example, we represent a value we retrieve from a database. The value could have not been there, so we use the lookup function that produces a value of type maybe to be able to return nothing if we can't find the value inside the list. So if we run this, we see that 8 saved it 2 is just 4, and 8 saved it 0 is nothing, so it didn't crash. And we see that the lookup function takes a key and a list of key value pairs, tries to find the key inside the list, and if it does, it returns just the value, or if it doesn't, it returns nothing. So in this case, if we look up the key Eren in the list, the function will find that Eren is indeed in the list and return 10, which is exactly what we have here. Just 10 is a maybe value because if the key wasn't inside the list, it would just return nothing. Now, imagine that we need to apply the calculate function to a bunch of maybe values. So let's run this. So we have the calculate function. So before learning about functor and applicative, we could have defined a function that takes 3 maybe values and applies calculate to them like this. We create a new calculate maybe function that takes 3 maybe values, and we manually handle all possible failure cases. So in the case that the first one is nothing, nothing. If it's just A, we have to check the second one. If it's nothing, nothing, else we have the V, then we need to check the third one. If it's nothing, nothing, but if the third one is actually there, we have all 3 values, so we can apply the calculate function to A, B, and C, and then wrap the results in the just to have the correct type. If we run this, we get the correct results. We see that the calculate maybe applied to 8 safety 2 as first parameter, pure of 2 as second, and value from database as third parameter returns the correct result. But this has several disadvantages. One is that we have to create the new calculate maybe function. Another is that calculate maybe only works for maybe values. And finally, we have to write a massive block of code pattern matching with case expressions to handle the maybe values 3 times. The same code repeated 3 times. But now that we have functor and applicative, we can do the same in a one-liner. If we run this, we get the same result. We don't have to create a new function. We can replace the values we apply calculate to with any type that is an instance of applicative, and we don't have to handle the failure cases by hand because that is handled by the operators under the hood. This is what we achieve code-wise. But there's a different way to look at this code. We can also think of maybe as a type that provides the simulated effect of exception handling. In that case, the apply operator is a way to sequence effect and combine their result. As you can see in the calculate maybe function, we sequence the exception handling one after the other and then apply the calculate function at the end to combine the results. When we apply functions using the applicative operators, also called applicative style, we do the same as in calculate maybe, but in a hidden and more convenient way. That's why it's understandable for you to be confused when I'll tell you we can think of it as an effect. If you can clearly see in the body of calculate maybe that it's actually just pure code. In Haskell, we have a bit of a loose concept of effect. Sometimes the same code can be thought of having an effect or not, depending on how you interpret it. So, to make it as crystal clear as possible, here are a few key clarifications that will save you a lot of time and headaches. Haskell has both real effects and simulated effects. Real effects are impure and unpredictable. For example, I/O effects. Simulated effects look impure when you use them, but actually they are pure under the hood. For example, the maybe type that we just saw. Simulated effects look impure because the computations are hidden from us behind types and operators. So from the point of view of the user of those types and operators, it looks like they are running side effects, but it's actually pure code that they cannot see. Another worthy clarification is that independently of whether they are real or simulated, all effects have an associated type and at least an applicative instance. Usually, they also have a monad instance as well. So, applicative and monad are the interfaces for effects. You can think of these type classes as the boundary between what is and what is not usually considered an effect. As a side note, don't worry about monad yet. We will cover it in a future lesson. Just know that monads have a close relationship with applicative and the concept of effects. Let's see a few examples. We have the identity applicative that provides no effect. We also have the maybe applicative that provides the simulated effect of a computation that might fail. An evolution of that is the either applicative that provides the simulated effect of a computation that might fail with an error message or some context as to why we had an error. We also have the least applicative that provides the simulated effect of a non-deterministic computation. A non-deterministic computation is a computation that can have 0, 1, or multiple results at the same time. These multiple results at the same time means that if we return a list with multiple elements, each element on the list is a result. And finally, an effect we already knew is the I/O applicative that provides the real effect of interacting with the world. These are examples of effects in Haskell. We will discuss more effects in later lectures. But let's stick with these ones for now to avoid overwhelming ourselves. Now it makes sense why we call pure the function that we use to lift values to the applicative functor level. It's because we are embedding a value without an effect, a pure value into an effectful context. Once again, all we do with pure is to wrap the value with the correct expression, the same as we have been doing during this lesson. That has not changed. It's the way we think about what we are doing that changed. We will talk more about effects when we cover monads. For now, with this new point of view, let's finish this lesson the same way we did with the functor one, by exploring the extra functions we get for free with Applicative and presenting the type class and how it's defined in the base library. So, the first functions we will take a look at are the lift functions. We have the lift_a, lift_a2, and lift_a3 functions. These three functions are the same as we defined earlier as fmap, fmap2, and fmap3. They take functions that take 1, 2, and 3 arguments, unary, binary, and ternary functions, and lift them to work at the applicative functor level. Their names start with lift because we're lifting functions. Then they continue with capital A because we are lifting them to the applicative level, and end with the number of arguments the lifted function takes. You will encounter functions with this naming convention regularly since it's used all over the base library. It seems like a bad joke, I know. I just told you that we don't need to define functions like these ones. And we don't. As you can see in the definitions, we can write any of them using only applicative style. Lift_a is pure of the function applied to the first parameter. Lift_a2 is f-mapping the function to the first parameter and then applying the result to the second parameter. And lift_a3 is just lift_a2 applied to the first three parameters, which is the same as this, but then applied to the last parameter, the third parameter. And if we run this, let's run it. Lift_a of +1 applied to 1 and 2 is 2 and 3, just 3 is 4. Lift_a2 plus applied to two lists, the list of 1, 2, and the list of 3, 4, gets 4, 5, 5, and 6 because we are adding all possible combinations. 1 plus 3 is 4, 1 plus 4 is 5, and then 2 plus 3 is 5, and 2 plus 4 is 6. Lift_a2 of plus applied to right 2 and right 3, we get right 5. And the same for this combinatory function and lift_a3. So we have lift_a3 applied to a function that takes 3 parameters, and we provide the 3 parameters, we get the correct results. So these 3 functions are the same as using the applicative style with just the pure and the apply operators. But there are reasons as to why we have these ones. So maybe if we wanted to design Haskell from scratch with what we know now, we wouldn't have these functions. But there are also subtle, non-historical reasons as to why we have them. On one hand, because lift_a and fmap are the same function, we could implement first the applicative instance of a type and then implement the functor instance defining fmap equals to lift_a, meaning fmap as a synonym to lift_a. It seems counterintuitive because functor is a superclass of applicative. But the same as we have mutually recursive functions for the EQ type class, the compiler doesn't care as long as both instances are defined and we eventually reach a base case. So if, for some reason, defining the pure and apply operator is easier than defining fmap, you have the option of doing this. That's also why we use pure and the apply operator instead of fmap to define lift_a. If we didn't do that and use lift A equals fmap, then you will define fmap using lift A and lift A using fmap, and you will get an infinite recursion. If all that didn't make any sense, it's okay. It's an implementation detail, not crucial, and it's not a new concept. Moving on to lift A2, it turns out that some functors support an implementation of lift A2 that is more efficient than using fmap and then the apply operator. In particular, if fmap is an expensive operation, you can redefine the standard definition of lift A2, which I'm showing you right here using fmap. So you can redefine this standard definition to avoid using fmap to get a more optimized definition. That way, it will be better to use the optimized lift A2 than to fmap over the structure and then use the apply operator. We don't really care about optimizing our code for now, so for us, it's just a shorter way of lifting a function. And finally, lift A3 is there because counting to 2 feels incomplete. Jokes aside, in most scenarios, you should use fmap instead of lift A, and if you have to lift a binary or ternary function, feel free to use lift A2 and lift A3 or the applicative style, whatever you like best. Now let's move on to more interesting ones. Analogous to the functor case, we have these two operators. One to sequence actions discarding the value of the first argument, and one to sequence actions discarding the value of the second argument. We said that the apply operator sequences effects or computations or actions and combines their result. Well, these ones do the same, but discarding the value produced by one of the inputs. Notice that the same as with the analogous of the functor type class, the arrow points to the value you will get. So in the case of the first one, we take two applicatives and we sequence them using the apply operator, but we use the functor operator that discards the value of the right to evaluate the first applicative, ignore the result of the value, and return the ID function that applied to the second functor, it won't change a thing. So just 2 sequence to just 3, ignoring just 2, returns just 3. And if we start with nothing, it doesn't matter how we sequence it, we get nothing, of course. And in the second case, we use lift A2 to simplify because we already have this, applied to the const function. So we take 2 applicatives and return the value of the first. So in this case, we evaluate just 2 and just 3, but we return the value of just 2. So in this case, there you go. It seems silly to discard values. But, as we said before, if we think of applicative as the interface for effect, if you want to perform the effect or computation but you don't care about the results, like for example printing to the console, when you print to the console, you get back the unit. You don't care about the unit, you have no use for unit. So in that case, you can use one of these to ignore the results, the value result. Then we have the reverse application operator. This operator does the same as the apply operator, but first takes the applicative value and then the applicative function. If we take a look at the typed signature, we see that it's the same signature as the apply operator, but instead of taking function and then value, it takes value and then function. So it has its arguments reversed. For that, we use lift A2, but instead of using const, for example, like we use to ignore the first value, in this case, we leave the function that takes 2 values, flips them, and applies the second to the first. This operator is helpful in cases where the values you get are okay, but the effects are in the wrong order. In this example, we are using IO effects. The IO type is an instance of applicative. So in the first attempt, we evaluate the first applicative while performing the side effect of retrieving the value from the database. And then we evaluate the second applicative that performs the side effect of saving the value in the database. After running both effects, we apply the ID function to the result of the second effect, which is a unit, and that's it, we get unit as a result. The problem is the effects are in the wrong order. We first need to save the value to the database so we can then retrieve it from the database. But we cannot just change the order of the arguments. The result of the first effect is a function, in this case the ID function, and the result of the second effect is the constant value unit. One is a function and the other is a constant value. So what do? One solution you can think of is to use the flip function here. The flip function, as we already learned, is designed specifically to flip the arguments of the function. And that's what we see here in this second attempt. Now we have first the applicative that saves the value in the database, and then the applicative that retrieves it from the database. The code looks fine, but if we evaluate the expression, we see that we first perform in the first attempt that we didn't do anything, we just used the apply operator. We have first retrieve value and then save value. And in the second attempt that we flip the arguments, we still perform first the side effect of the retrieving the value to the database and then to save the value to the database. We are still performing the effects in the wrong order, even when we are passing the arguments in the correct order. This is because when we evaluate the expression, we reduce the flip expression and end up having the same final one. The flip function only changes how we provide the values to the original function, but not how the values are evaluated. So even if we write the values in a different order, the effects run in the same order. This is the problem this new operator solves. It not only flips the arguments, but also resolves the effects in the order they are presented. So now, using this new operator, we can finally first save the value in the database, as you can see here, and then retrieve the value from the database, as you can see here. This is the main use case of this operator. But we still have more operators. Another useful one is the forever function. As you can see by the definition, we get an applicative of type FA, perform its effect, ignore the results, and recursively run forever with the same applicative. So this is the same as applying the applicative, ignoring the result infinitely forever. This function will never stop by itself. It's the first time we have a forever looping function that is actually useful. Now that we have applicatives, we can perform effects. So now, infinite loops make sense because we are not interested in what the function returns, but in what the effect does. If we run this cell, for example, we get a prompt because we are running the effect of getLine. And if we write something, for example, first, it performs the effect and then it runs again. Now we get a new getLine, and then second, third, fourth, and it keeps going and going and going. It will never stop. A common use case for this function is, for example, to have a server forever listening to client connections. In that case, you want the server to keep listening as long as you have it running, so you use an infinite loop. Another cool thing we can do with applicative is to have conditional execution of expressions. For example, here we have the when and unless functions. the when function takes a boolean and an applicative that returns unit. This function executes the applicative expression only when the boolean is true. And we have the counterpart unless that takes the same boolean and applicative, but it executes the applicative unless the boolean is true. I'm not showing you the implementation because you will have to implement them yourself on the homework. But an example will do fine. Here are all the possible cases. So we can have for the when either true or false, and for the unless either true or false. In all cases, I'm printing when is and the value of the boolean. This will help you figure out how they work. So if we run this, we see that the effect, the applicative, only runs when is true, so here, and unless is false, here. The other cases, when is false and when unless is true, the effect is not performed. So we are not evaluating the applicative. And that's how they work. And you might have noticed that I'm importing the functions from control.monad, where most of applicative functions are in control.applicative. That's because these functions, and other we'll discuss later, were constrained by the monad type class before the applicative type class was fully integrated into the base library. Because maintainers wanted to minimize breaking changes, these and other functions were left in the monad module, but with the applicative constraint instead of the monad constraint. So, for all intents and purposes, these are applicative functions that happen to be in a different module because of historical reasons. If you think we are talking a lot about monads for a lesson about applicatives, it's because before, this behavior of sequencing effects was found in the monad type class. So the applicative type class stole a lot of work that used to be done by the monad type class. And there are still a few loose ends sprinkled around the base library. Coming back to the when and unless functions, to give you an example that is actually practical, take a look at this. Here we have the print even numbers until 0 function. It takes an integer and returns an IO of units. You can almost read the expression as if it were plain English. The print even numbers until 0 function takes a number, and when it's even, it prints it. Then, unless the number is less or equal than 0, it recursively calls the print even 0 numbers until 0 function with the number reduced by 1. So if we apply the function to 15 and we evaluate, we get all the even numbers from 15 until 0. This is just one example of things you could do with these functions. And I think those were enough clues for you. So let's keep going. We have still 2 functions to go. A really cool one is the replicate m function. I'm going to zoom out just a bit so it fits. The replicate m function takes an int that we name n and an applicative that we name action. Then it executes the action n times and returns an applicative with a list containing all the results. Same as with the when and unless functions, the replicate m suffers from historical baggage. It has an uppercase m at the end, signaling that it works with monads. And the type variable constrained by applicative is a lowercase m, signaling that it used to be a type variable constrained by monads. If we will write the base library from scratch today, we will likely call this function replicate a and use f for the type variable. But do not let that distract you. For you, this is an applicative function, same as the others. In the definition, we have 2 cases. If the number is 0 or negative, we shouldn't do anything. So we return an empty list lifted to the applicative level using pure. Or in other words, we embed a pure empty list in the effect of the applicative, whichever might be. Otherwise, we have a number that is larger than 0. So we run the action and add the result to a list. We can do that easily thanks to the fmap and apply operators. And since we have to accumulate the results in a list, we concatenate them. So we use fmap to apply the pure cons operator to our applicative, and then we apply the partially applied cons operator at the applicative level to a recursive call of replicate m with a reduced n. So we will keep lifting cons operators and applying them to the result of evaluating the applicative until we reach 0, and then return the empty list. At that point, we have a list of all the results concatenated in a list, which is exactly what we need. Let's see an example. We import the replicate m function from control.monad, and we create the get3answers function. This function takes a string, which is the question we want to ask, and returns an IO function that, when evaluated, gives you back a list of all the answers someone provided. Let's see how we implemented it. We take the question as a parameter, and then we use this sequence operator to first print the question, ignore the result, and then use replicate m to run the getLine effect 3 times and get the result as a list of strings. So if we run this, we apply the get3answers functions to what are your 3 favorite Pokemon. If we evaluate this, we get the prompt of the getLine. So we'll start with the obvious, Pikachu. That's the first one. Then we use Mimikyu. And finally, we evaluate the last getLine effect. So we provide some response. And as soon as I finish the side effect, we will get a list with all 3 answers as a string. And now we can do whatever we want with this list. We also have a variation of replicate m called replicate m underscore. The underscore at the end is another naming convention followed by many functions that deal with effects. If a function ends with an underscore, it means that it ignores the result and returns the unit. So, if you only care about the effect and not the value, you can use a function that ends with an underscore, if available. It's usual to have the same function with and without the underscore. Both do the same, but one returns a value and the other just returns a useless unit. I'm again not showing you the definition because you have to do it yourself in the homework. But now that you know this, you know what replicate m underscore does. It does the same as replicate n, but returns the unit instead. Here's an example of why would you want to do this. Here we import the replicate m underscore from control.monad, and we use it to create the get and save 3 answers function that it also takes a string and returns an IO, but this time this IO, when evaluated, returns a unit. And the implementation is pretty much the same as the get3answers function, but we are using replicate m underscore. That means that we won't get the responses back, but we don't care about that because the applicative that we are evaluating now is not longer just getLine. It's a save to database function applied to getLine. Of course, we are going to leave this save to database function implementation to your imagination. But now, knowing that we save the response in the database as part of the effect of getting the answer, we have no need anymore to return the answer as a value. So now, if I run this new function, and I say, for example, Pikachu, As soon as I hit enter, everything disappears. Every time I input an answer, the effect of getting the answer and saving it to the database was run. So when I wrote Pikachu and hit enter, it got the answer and saved it to the database, and then replicate m_run again the action. I perform the input, hit enter, and then it run, save to the database, and run again the answer 3 times. And there are many more functions like these ones that we could talk about. But we're going to leave it here for the sake of time and because after all we discussed so far, you can search for them in the documentation by yourself and quickly understand what they do. So, after all this work, this is what we got. It's a lot, so I had to split it into 3 different slides. We have the applicative functor definition. Now that we know how to think about applicative as effects, we can change a bit our interpretation. So we can say that an applicative is a functor with operations to embed pure expressions and sequence computations or effects combining their results. If we look at how applicative is defined in the base library, we will see that several of the functions we just talked about are part of the type class, and others that we don't see here are not. As with functors, we don't care about that distinction since they all come for free when you define the applicative instance. Another important thing to notice is that we have mutual recursion between the apply operator that uses lift a2 as part of its definition and lift a2 that uses the apply operator as part of its definition. The rest of the functions, except for pure, are defined using one of those. So at the end of the day, we have to provide only pure with either the apply operator or lift a2, whichever we prefer to implement. On top of that, every type that has an instance of this applicative type class has to respect these laws. And finally, by creating an instance of the applicative type class, we not only get the behaviors of the type class itself, but we get a ton of utility functions that are not part of the type class, but are available in the base library. You just have to import either control.applicative or control.monad. It's dramatic the number of functions we unlock by creating an instance of applicative. So many, in fact, that we couldn't cover all of them. The power that this abstraction provides is huge. Use it responsibly. And that's it for today. We introduced only one more abstraction today, but we also talk about how we can interpret types that are instances of this abstraction, the applicative type class, as effects. If that didn't quite click, it's okay. We will talk more about effects in the monad lesson. For now, the best will be to get comfortable both defining and using operators independently on how you think about it. And for that, make sure to do your homework, and I will see you in the next one.